So I will end by 4:30, right?
Yes, sir.
Till last, I think last week we missed because of the lab classes. Uh, I think I had to power angle characteristics. Is it okay? Is it in line with the thing what you have, or else I have completed this thing also? I had already completed this thing also. I don't remember actually. So can anybody say if it up to how much it was not? Power angle characteristics was covered or not? Constructional features of alternators, right? Regarding your salient pole machine, cylindrical rotor machine, and all, and different different categories like L by D ratio, etc., etc. And then we learned actually that the factors affecting voltage regulation. Voltage regulation started. Now factors affecting voltage regulations. From there we had learned about that armature reaction. Then after that methods to calculate voltage reaction, and then within that actually we had studied different characteristics of alternators. Okay, short circuit, open circuit, zero power factor, etc., and different methods of calculation of voltage regulation. Now after that we will go for power angle characteristics. Of course we have studied phasor diagram also in between. Okay, so those portions are covered. Now we take a new chapter, that is power angle characteristics. Power angle means actually, this angle means load angle. So the load angle, if you remember, I told one thing, the angle between the no load EMF and the terminal voltage, E0 and VT. The angle between E0 and VT was told to be load angle. Okay. So the load angle is positive in case of generator, as because it is generating electrical power, right? Positive means E0 is leading VT, right? If I take VT as reference, terminal voltage as reference. Now E0 will be lagging VT when it is working as a motor. So then in that case, actually power will be absorbed by the machine. So now we to in order to find out characteristics, means actually equation between P and delta. That means the power and this load angle delta. So we are again taking help of the equivalent circuit, right? So I think this slide is visible to you, na? This slide.
Yes, sir. Yes, sir.
Okay. So now just a minute, someone is again come. Right. So now, actually, if you see, this is the equivalent circuit, per phase equivalent circuit of the machine, where we have E0. We have assumed it as a generator. So E0 is leading by an angle delta, and VT is at an angle 0°, right? So this is no load EMF, and this is the terminal phase. And current is flowing from the machine to the load. That is why it is directed outward. And then we have, that machine impedance or synchronous impedance here, which is RA and JXS. RA and JXS. From that, if we want to calculate power at the load terminal, so you will take use of the simple equation VT into IA conjugate. Okay, VT IA conjugate, so that you know. And for that, we know actually VT, but what is my IA? So I have to derive IA from this KVL equation. Now KVL equation, if you look at KVL equation, this loop having VT, IA, RA, JXS, E0, and current IA. So you get this equation. Applying KVL in this loop, you get VT equal to E0 minus IA into RA plus JXS. It's quite simple actually. Just you have only one loop and you just calculate VT E0 at an angle delta minus A into RA plus JXS. So from here you can get the value of IA, which is actually E0 minus VT, E0 angle delta minus D by this RA plus JXS we can write as in polar form Z dash angle theta S. So now when you compute power, so you get Vt into Ia conjugate. So Vt means Vt angle 0 degree. So Ia conjugate means just I have computed here, like E0 delta will become, you know what is a conjugate, complex conjugate of a vector. So E0 angle minus delta. So Vt 0 will be 0 only. And then Zs angle minus theta s. Then if you multiply these two, you get this term E0 Vt by Zs theta s minus delta angle minus Vt square by Zs theta s. So this gives you the complex power equation, total power equation in complex form. That means it has got a real part and an imaginary part. So I am going to the next page. So I think the page has changed. Okay. So then the total power is actually P plus JQ. This is active and the reactive power. So imaginary part is actually denoted by Q, and it is reactive power means JQ. So then if you have, it will be actually E0 Vt by Zs cos theta s minus delta. So from here you get cos theta s minus delta, and cos theta s is the real part, and sin theta s minus delta and sin theta s is the imaginary part. So we have E0 Vt by Zs cos theta s minus delta minus Vt square by Zs cos theta s as a real part, and then J E0 Vt by Zs sin theta s minus delta minus Vt square by Zs sin theta s as imaginary part. So now from that you can equate the active power like P equal to the real part, which is actually E0 Vt by Zs cos theta s minus delta minus Vt square by Zs cos theta s, right? So again, if you take help of impedance triangle, you get Ra, Xs and Zs. So here is your theta s now. So the other angle is denoted by alpha s of this right angle triangle. Now for which you get alpha s plus theta s equal to pi by 2. Because I mean simple angle equation of triangle, you get alpha s equal to pi by minus theta s, or theta s is pi by 2 minus alpha s. So if you put it here theta s, this becomes pi by 2 minus alpha s minus delta, and then cos theta s from here is Ra by Zs. So you just substitute these two. So pi by 2 minus alpha s and Ra by Zs. So you get sin delta plus alpha s, right? E0 Vt by Zs sin delta plus alpha s minus Vt square by Zs square Ra. Because cos theta is Ra Zs. So you get this equation as the power equation, which is the function of delta. That is the sinusoidal function of delta, right? So now we can have two cases. Now in the first case, as I said earlier, that usually that synchronous impedance, if you can be approximated as only that synchronous reactance part, because RA is very less compared to XS. So if we do that, if you do that approximation, we get actually XS equal to ZS, right? Because RA is 0. And then here alpha S will be 0 and theta S will be pi by 2, right? So now if you put here RA equal to 0, so this vanishes, and then alpha S 0 means it becomes only E0 Vt by X sine delta. It will be XS, although I have written ZS, but ZS equal to XS, okay? So it will be E0 Vt by XS sine delta, right? E0 Vt by XS sine delta. This is actually the equation for power. Now, if you plot it, you get this kind of sinusoidal curve, for which when you plot it in the negative delta region, it becomes the curve for the motor, and it's for the positive delta region, it is for generator, right? So now you can calculate maximum power also. So you can calculate having where the slope of P is 0, that means dP d delta is 0, will give you cos delta equal to 0, that means delta M is pi by 2. So this is the maximum power angle. That is the angle for maximum power. So delta M equal to pi by 2. And then for maximum power, you put pi by 2 here, so you get E0 Vt by Xs. So P max is E0 Vt by Xs. So this is for the case where we neglect resistance. Okay, armature resistance is neglected. Now I am into the next page. So you see, an RA gets included. Supposing we are going to see it for total thing without neglecting RA. So then your power equation becomes the previous one without having any term neglected or made zero, right? So it is E0 Vt by ZS sine delta plus alpha s minus Vt square by ZS square Ra. So this has got two parts. One is a sinusoidal part and one is a constant part, right? So constant part is a negative one. So you can just plot it here like this. This is minus Vt square by ZS square Ra. And then this part, if you see, it can have several situations like at delta equal to zero. So this can E0 Vt by sine alpha s, right, at delta equal to 0. Actually, this is a sine curve with leading angle alpha s. That is true. It is a resultant. This angle is alpha s, right? Where I am putting the arrow, right? So, but here, if you see, P1 is E0 Vt by s into sine alpha s, which is at delta equal to 0. Now, sine alpha s again, if you take the integral here, so sine alpha s is what? Again, R by ZS. Sine alpha s is R by Z. So if you put here by ZS, it becomes ZS square RA minus total power is actually Vt square by ZS square RA. Someone is again come. Oh no. Okay. Square by ZS square RA. So now you take common like RA by ZS square. So you get Vt RA by ZS square into E0 minus Vt. So showing that how you can represent it actually, the resultant one. Now if you see, if you try to plot resultant one, so this is the first P1 actually. This is the plot for P1, which this angle is alpha s. But when actually you see the total plot, you see it is becoming at delta equal to 0, the magnitude is Vt square Ra into E0 minus Vt. So from where you can have three cases. That means you can have an excitation which is equal to Vt, right? Which is known as normal excitation. So then in that case, P at delta equal to 0 will be 0. So the resultant curve will pass through the origin, right? E0 equal to Vt, right? This curve. Now it can so happen that E0 is less than Vt. That means under excited situation, right? It can happen during normal operation of the alternator also. So when it is under excited, so P becomes negative. That means this becomes the resultant curve, E0 less than Vt. Now when E0 greater than Vt, it is overexcited. So you get P positive at delta equal to 0. That means you get this curve, upper one. So E0 greater than Vt, right? So have three such situations and where the resultant can be like this. Otherwise, you can plot individually this one, P2 and P1, right? So this way. Now again, you can find maximum power situation in a similar fashion. You can make it delta equal to 0. So it gives you cos delta plus alpha is equal to 0. Delta m actually delta for maximum power is equal to 0. This cos pi by 2. So then delta m becomes pi by 2 minus alpha s or theta s, right? As per our impedance triangle, delta m becomes theta s. So the maximum power will occur at theta s instead of 90° when RA was excluded or RA was neglected. Okay. So here maximum power is at theta s. Now if you put the magnitude, this theta plus alpha s or delta plus alpha is equal to pi by 2. So then this gives you the magnitude of maximum power, that is actually P max equal to E0 by Z dash. This will be 1 because sine pi by 2 minus Vt square by ZS square Ra. So it is lesser than what we got when we neglected Ra. So this is the case. Now consider the motoring case again. When you consider the motoring case, that means motoring is for the negative delta region, this portion, left side of the y-axis or left side of the p-axis, right? P delta curve, P versus delta. So I go to the next page probably. Oh, it is not. Uh, okay, motoring is there. But okay, motoring, this portion is not there in the next page. So I saw it from here only. So in the motoring situation, you get E0 and VT and all things same, but current is reversed because machine will be absorbing current. Instead of delivering current, machine will be absorbing current. So in that case, your EMF equation, rather the voltage equation applying KVL, will be just a little bit different because the current is reversed. So in that case, VT will be E0 plus IA into RA plus JXS. E0 plus IA plus RA into JXS. Okay. So then E0 will be what? E0 will be VT minus IA into RA plus JXS. Okay. Okay. E0 will be VT minus IA into RA plus JXS. Then I have drawn for your clearer understanding the phasor diagrams also here. Now, if you see if you see that this is your reference phasor VT minus IARA minus JIAXS will give you E0 because delta is negative here. Okay, so this is shown for lagging power factor. Okay, when power factor is lagging, so IA is lagging VT by some angle theta. Now this is the MMF phasor. So MMF is actually now say FF is the no load MMF. No load MMF will lead the no load EMF by 90°. So instead of FF plus FF, which we saw for the generator, it will be FF minus FA because current is in the reverse direction. So FF minus FA is resultant. So here resultant is more. So that is why VT is more compared to E0. Now here, if you see a leading power factor condition, this is IA. Now VT minus IRA minus JIAXS E0 here. So E0 will be larger than VT, and also you see here also it is lagging by an angle delta, that is minus delta. That means it's a motoring operation. It is absorbing electrical power. So then again MMF phasor, you see E0 is here, FF is here, so FA minus FA is here, FR. So resultant is lesser, so that is why VT is lesser compared to E0. So actually you get the phasor diagrams of lagging and leading load both for motoring operation. For generation, I think I had shown earlier. So now based on that, you can again find out the maximum power situation for motoring. That means there also the power equation is same, but delta is minus delta, right? So if you see, if you make dp d delta equal to 0, so you get again cos delta m plus alpha s is 0. So since total angle is negative, so it is actually cos minus pi by 2. So delta m is minus pi by 2 minus alpha s. So you get here in this plot, it appears an angle which is minus pi by 2 minus alpha s. Okay, this is minus alpha s, and again from here minus alpha minus pi by 2. Okay, so minus pi by 2 minus alpha s, or if you can put alpha s equal to actually pi by 2 plus minus theta s, pi by 2 minus theta s, there is something wrong here. This will be pi by 2 minus theta s plus pi by 2 minus theta s. So you get minus pi by 2 minus pi by 2. This is minus pi plus theta s. So you can write any of the two. Either it is minus pi plus theta s or minus pi by 2 minus alpha s, whichever is possible. So then if you put the same angle here, right, for maximum power situation, this is minus pi by 2, this will be minus pi by 2 actually, then actually because delta equal to minus pi by 2 minus alpha s, so this is negative, so you get actually total negative power. This is minus E0 VT by ZS minus VT square RA by ZS square. Or you can write in a different way by rearranging the terms, like minus VT by ZS into E0 plus VT RA by ZS. Okay. So I think this is clear for you. So anything which is not understood, is it, I mean, can you just tell me which is this portion? Is it all right? আছো সবাই?
Yes, sir. All right.
ঠিক আছে, একদম সিম্পল, you can say simple. So then we go for the reactive power. So if you see reactive power, I derived this one here in this page. Now Q usually is this part. That means the imaginary part. E0 Vt by Zs sine delta sine theta s minus delta minus Vt square by Zs into sine theta s. So same I have written here. E0 Vt by Zs sine theta s minus delta minus Vt square by Zs into sine theta s. Okay, someone is phoning. Just 1 minute. So actually, you see that this one. So this is Q. So E0 Vt by Zs sine theta s minus delta minus Vt square by Zs into sine theta s. Again, we will do the same replacement like delta equal to pi by 2 minus alpha. Sorry, theta s equal to pi by 2 minus alpha. This will be theta s. Theta s. So by quickly writing, so I have missed out many things. So theta s is actually pi by 2 minus alpha s. And then again, from the impedance sine theta s, if you again look back at the impedance triangle, so sine theta s will be actually xs by zs, xs by zs. Okay, sine theta s. Again, I go back. So this is sine theta s minus vt square by zs into sine theta s. So I replace here e0 vt by zs sine pi by 2 minus alpha s minus delta minus vt square into xs by zs square. So just xs by zs I have replaced here in place of sine theta s. So again q becomes e0 vt by zs cos delta plus alpha s minus vt square by zs square xs minus vt square by zs square into xs. So this is again the expression for the reactive power, right? Now again we go for the cases we considered, like initially Ra equal to 0, that is s is 0 and xs is zs, xs is zs. So you get q equal to, from this q equal to q equal to e to vt by zs cos delta, because alpha s is 0, minus vt square by zs xs, so vt square by xs. So e0 vt by xs cos delta minus vt square by xs. This is the expression for q. So again, if you try to plot this on the delta positive and delta negative region, so we get two parts here. So one is q1, one is q2. So q2 is the constant term, which is actually minus vt square by xs. Here, this is my delta axis. This is delta and this is q. Okay. So then this is actually, so I tried to make it very compact. So you have to understand it in a very clumsy manner, because otherwise there will be too many pages and I have to always shuffle the pages. So better I took I made it in a way actually. Huh? So then you have this is minus vt square xs equal to q, right? This one is the constant term, and the cosine term is this e0 vt by xs cos delta, right? Add both of them, you get the resultant. So at then delta equal to 0, at delta equal to 0, so you get actually e0 vt by xs minus vt square by xs. So again, if you take common vt by xs, so you get e0 vt. So there are three situations that can arise here again. So at the first situation is e0 equal to vt, that means normal excitation. So at delta equal to 0, it will be starting from 0 and coming down like this, and in the delta region also like this. And when overexcited condition E0 greater than Vt, so it will be E0 greater than Vt positive, and it will be cosine curve like this, and another cosine, shifted cosine in the y direction. And then E0 less than Vt under excited condition, again shifted cosine. That means at 0 delta equal to 0, you have negative q0, rather q, and then it is shifted in the negative q axis, so like this in the both motoring and generating region. Generating is the right side and motoring is the left side. So now if you want to calculate the maximum reactive power condition, that is dq delta equal to 0, will give you, this is sine delta equal to 0, and then it gives you delta m equal to pi. right? Sine delta m equal to 0. That means delta m equal to pi. And for motoring case, it is actually delta m equal to minus pi. The same way, actually, minus delta, right? And value of q max is actually, for generating, if you put cos pi, it becomes minus 1. So then it is minus e0 vt by xs minus vt square by xs. And if you take common, minus vt by xs into e0 plus vt. So it becomes, it gets added up, right? It gets added up because both are negative, right, in the motoring and in the generating part, and motoring part also like this. Same for generate, same as what we get for generating q max equal to, because cos minus pi and cos values are same, right? So minus b vt by xs into e0 plus vt is a maximum power, maximum reactive power. Now, in case of stress, where we consider the resistance also, armature resistance also, that means Ra not equal to 0, then you get the total expression like this: E0 Vt by Zs cos delta plus alpha s minus Vt square by Zs square into Xs, right? So then again you get actually there are two terms. One is a constant term, one is a shifted cosine term. That means delta x delta cos delta plus alpha s is this one, q1. So it is shifted by alpha s minus alpha s here in the negative delta region. So I forgot to mention, this is positive delta, this is negative delta, right? Then you go again, same manipulations. Say at delta equal to 0, you get cos alpha is this, and again cos alpha is xs by zs. So you put that, you get bt xs by zs square into e0 minus bt. And at delta equal to 0, you get 0 reactive power during, you can say, normal excitation, positive reactive power over excited condition, and negative reactive power at under excited condition. So you get a similar curve, only shifted by minus delta here. So then if you want to calculate that maximum reactive power situation, so it is actually dq d delta is 0. There is again sine and delta plus alpha s is 0. There is sine minus pi. So minus pi minus alpha s, minus pi minus alpha s. This will be actually, sorry, this is actually sine minus pi. So this is minus pi minus alpha s. Okay, this will be minus pi minus alpha s delta m. You just correct it yourself. This will be minus pi minus alpha s. So it is in the left side. Okay. And now if you put that maximum power situation, that means delta equal to minus pi minus alpha s, again cos minus pi is minus e0 bt by zs, right? Minus bt square by zs square xs. So same for motoring and generating, right? This is written here, minus pi minus alpha s in the next step. Okay, so here but somehow this minus sign is omitted. So this is minus pi minus alpha s for motor. Oh ho ho ho. So this was generator. I'm sorry, for generator it is written. So this is, for generator it is sine pi, and this is pi minus alpha s. For generator it is pi minus alpha s. For motoring it is minus pi minus alpha s. It's correct actually. So same as motor and generator, minus bt by zs into e0 plus bt xs by zs. So now reactive power variation with delta, both active and reactive power variation with delta has been studied, and all this, mind it, all this has been derived for non-salient pole machine. That means cylindrical rotor machine, where we have concept of excess. Okay, concept of excess. Now you will see the situation when we use for salient pole machine. When same thing for salient pole machine, right? Now in salient pole machine, there is a basic constructional difference between say cylindrical rotor and salient pole machine. What I had we had told you earlier. Now, what is the basic difference? Means the rotor construction for cylindrical rotor is like this. So this circle inside, outside is the stator part, and this inner circle is the rotor part for cylindrical rotor. And for salient pole machine, this circle and outside is the stator part, and this salient pole is the rotor part, right? So these are the two constructional views, rather you can say sectional views of the rotor. For cylindrical rotor and salient pole machine. So now you see that we had studied when we had studied armature reaction. When we had studied armature reaction, so we saw that due to the load power factor, the position of the armature MMF actually varies. So it can be for unity power factor, armature MMF should be here, right? It will be working across the main field, considering the field is in this direction. Okay, so let us say we get a unity position. This is the field position for both the cases. This is the field position for salient pole. This is the field position for cylindrical rotor. Now for unity power factor, so if the rotor is rotating in this anti-clockwise direction for both the cases, now we have a unity power factor. MMF is here, armature MMF, armature MMF is here. It is working across. Now when the power factor is lagging, actually, so we have MMFs shifting from this position in the upward position, right? And when it is zero power factor lagging, it becomes magnetizing. It is here. It is shifting like this. When it is leading, it is shifting like this in the anti-clockwise direction, right? And when it is zero power factor leading, so it becomes entirely magnetizing. So the situation is same here. The question is, if you see that the magnetic circuit faced by this MMF is same everywhere, irrespective of the position of the MMF phasor for the cylindrical rotor machine. But the magnetic circuit faced by the MMF phasor is different in case of salient pole machine, because when it is here, you see air gap is minimum. When the MMF is here, air gap which is maximum, and in the other places which is in between, right? So therefore, even if the MMF becomes same, the amount of flux produced by this MMF for magnetizing or demagnetizing action becomes different in case of salient pole machine. It's a function of the position. It's the function of the position of the MMF phasor, right? So therefore, actually, the armature reaction effect will not be same. Everywhere for salient pole machine. So that is the major factor actually. That is why actually we cannot have a representation of a single synchronous reactance in case of salient pole machine. Synchronous reactance is the representative of the armature reaction effect. That means the flux which is produced under demagnetizing or cross magnetizing condition, right? So then actually the x becomes a function of the position, right? So that is why the theory actually, and it's known as Blondel's two reaction theory, has been formed. Professor Blondel. Now he actually did a very thing by actually defining two axes for this say MMF phasors or rotating phasors. Now, two axis means actually, now one axis is the field axis, right? Which is known as the direct axis, D axis. So here also field axis is the direct axis, D axis. And another axis is the quadrature axis, or the axis along the EMF, right? So EMF position is same for both the things, even if your load power factor varies. But the phasor changes, right? So he has defined two fixed axes. Like one is that D axis, the field axis, and another is the quadrature axis, the EMF axis or the axis quadrature to the field axis, right? Now, if we resolve this MMF phasor into two components, say wherever is the position, so that is one along D axis and another along Q axis, right? Another along Q axis. And as we have defined the axis, the air gap is fixed. Now air gap is fixed for the quadrature axis, it is this much, and air gap is fixed for the D axis, which is this much. So if we resolve this MMF phasor into two components, so one along D axis and another along Q axis, so the entire thing can be explained. That means the Q axis has a fixed reactance, synchronous reactance, and D axis has a fixed reactance. So concept of two reactances are coming. So the reactance along D axis is defined by XD, and reactance along Q axis is defined by XQ, right? So in that case, actually, the component of the EMF phasors will decide that how much actually the demagnetizing and how much cross magnetizing EMF is there, and actually you can represent this circuit with two fixed reactances. So this theory, by breaking the EMF phasor into two components, are known as Blondel's two reaction theory. Blondel's two reaction theory, this one, that field axis is the D axis, right? This is the D axis, and quadrature axis is the EMF axis, or the axis perpendicular to the D axis. Okay. Now, if this is resultant, so this is FAD and this is FAQ. That means that FA resultant has two components, one along Q axis, one along D axis. So this D axis reactance, D axis MMF will be represented by XD, and this FAQ will be dealt with XQ, right? So armature MMF can be resolved into two components for AD along D axis. Flux path is also fixed for both D and Q axis, and another along Q axis, which is FAQ, and XD is the D axis reactance and XQ is the Q axis reactance, and XD greater than XQ, as you see the air gap is more in for XQ, and these can satisfactorily explain reaction effects and other performance parameters of Cellier pole alternators. Okay, so that is why this is known as two reaction theory, Blondel's two reaction theory. Probably I have written here Blondel's two reaction theory here. Okay, so this is what. Now, based on which we will define two equivalent circuits. So ED and EQ, and this is RA JXQ and Q component of current IQ, and EQ is ID RA JXD. So you get actually Q component of D component of ID. Okay, so this way we can have two equivalent circuits, one for D axis, Q axis, or Cellier pole machine. So now again, say current is resolved into two components. So then you can have the Phasor diagram like this. So it is shown here. This is VT. You see, this is VT and this is IA. So in this portion, this is IA, right? This is IA, and which is lagging by VT. So IA can be resolved into two. So this is your EMF phasor. EMF phasor, it is Q axis, and perpendicular to this will be D axis. So IA is resolved into two components, ID and IQ. So actually, VT plus JIDXD, we have neglected initially. VT plus JIDXD plus JIQXQ will give you E0. So VT plus here JIDXD plus JIQXQ will give you E0. So then E0 is leading VT by say some angle delta, load angle delta. So for lagging power factor without armature resistance, so we can explain this with this EMF equations. So E0 will be V plus JIDXD plus JIQXQ, VT plus JIDXD plus IQXQ, because ID and IQ are actually two components along D and Q axis, and we have got separate D and XQ for both of them. Okay, so then the EMF equation can be written like this: E0 equal to VT plus JIDXD plus JIQXQ. Now, if you consider resistance, so it will be just multiplication by IA into RA plus JIDXD plus JIQXQ. Now, IA is actually ID plus JIQ, ID plus JIQ. So we can have ID RA plus JIQ RA plus JIDXD plus JIQIQ. Sorry, JIQXQ. So here it is VT. So ID is here. So JIDRA plus JIDIQRA, JIQRA, and JIDXD, and here it is JIQXQ. But actually E0 here. Now, or you can directly write E0 equal to IRA plus JIDXD plus JIQXQ. So this way you you can draw the Phasor diagram or draw the impedance EMF equation for EMF equation for salient pole alternators. Okay, so I think if I try to cover this power angle characteristics, it will be again taking some time. So I think we'll cover next day. Power angle characteristics of the salient pole alternator. So next
Okay,
day I
sir.
have to prepare material also. So okay, so till now I think you tell me whether you have understood or something still remaining. Any conceptual gap if you have. It's clear to you.
Yes, sir.
Okay. So okay, so next day after covering this class, probably I will be sending you this materials. This material actually, what I could prepare only is a indicative material, but you can read based on this. Or if you have already noted down something, I do not know. You should have had noted. But anyway, I'll be sending this one. Okay.
Okay, sir.
Okay. So I'm leaving. Okay.
Okay,
Thank
sir.
you, sir.
Thank you, sir.